class we discussed about how we can create the uh, the symbols and the elementary details of your AND gate. So by using a Nmos technology and by using a Cmos technology and by using a BiCMOS technology and the associated symbols diagram and associated stick diagram. So all those details we studied about in the morning class. So now what we are going to study is, so the same thing we are going to see for the NOR gate. Okay. So why? Because NAND and NOR we call it as a universal gates. So by using this NAND and NOR, we can able to simulate all type of basic gates, or we can able to simulate the Boolean expressions. So therefore, it is necessary for us to know the symbol logics and the associated stick layout diagrams for the NOR gate. Okay. So you can see here the diagram for the Nmos transistors, how we can implement this NOR gate. So we have made use of the depletion mode transistor, that is a Nmos transistor, followed by the NOR gate. So the NOR gate Boolean expression is nothing but A plus B, a complement of that we need to take. So it is nothing but negation of OR gate, we call it as a NOR gate. So therefore negation A plus B. So A plus B means in Nmos technology they will be in a parallel. So you can see the first diagram, that is a circuit diagram Nmos NOR gate. So you have a depletion mode transistor, followed by you have a two transistors where you are giving the two input terminals, that is A and B, and their pull up and pull down transistor ratios. So it has been given, that is L into width where ratios we have given 1:1. Okay, so this is the circuit diagram for your NOR gate, and already we have written the that is a stick layout diagram for this NOR gate in the module number 2. So now if you want to implement the same thing by using a CMOS technology, that is a complementary metal oxide semiconductor technology means, then you will make use of the PMOS transistors and the NMOS transistors. So as I said, series in NMOS transistors will become a parallel in PMOS transistor, and parallel in NMOS transistor will become a series in a PMOS implementation. So you can see here in the NMOS by NOR gate, so you had a and B transistors, though were in parallel, whereas in the case of series they will become a in the PMOS transistor implementation they will become a series. Okay, so you can see here we have a demarcation line between your PMOS transistors and the NMOS transistor. So the terminals A and B have been interconnected, and to make it so that we can power on both the PMOS transistors and NMOS transistors simultaneously. So similarly, the terminal B, it has been powered on for your PMOS transistor and NMOS transistors. So that the output will be from this complementary metal oxide circuit diagram, you will be getting A plus B complement of that value. So if you want to design the same thing by using a BiCMOS technology, where we are going to make use of the bipolar junction transistors also. So the output of the CMOS technology has been coupled to your bipolar junction transistor, so that the transistors will be biased through the base terminals. Okay, so therefore if you want to bias these transistors in the BiCMOS technology means, then the output of the BiCMOS has to be given as a driver circuits, just for your BJT transistors. So you can see here the terminal output terminal of this BiCMOS has been coupled to the two transistors, as you can see in this diagram. Okay, so and whatever the combinations or the placement of these transistors you are going to make it, you should make sure that you are going to attain a minimum size when you combine all the transistors in a single silicon wafer. Okay, so for the NMOS transistor, that is by using 8:1 or 4:1 as ratios. By the using that ratios, you can design the system, that is a symbol. So the symbol diagram is no different, there is no differentiation between your NMOS NOR gate and the complementary metal oxide NOR gate. Only the difference is between the pull up transistor and the pull down transistors. So you can see here at the bottom of this you have a stick diagram which is associated with your NMOS transistor and a BiCMOS transistors. So since NMOS transistor you have a depletion mode transistor at the first case, so therefore you can see there is a implant is there in the stick diagram. Whereas in the second case, so since you are making use of this BiCMOS technology, that is a CMOS technology, so you should differentiate between the PMOS region and the NMOS region. So therefore we are making use of this demarcation line. And for BiCMOS technology, so since you need to have a connection, just wait a minute. Okay. So since you need to have a connections in the by Cmos technology, because you are operating both on the Cmos technology and the transistor technology, so you should make use of the contact cuts in order to connect your VDD terminal to your transistors logic. Okay, so this is how we are going to make use of the elements, means it may be AND gate, OR gate, XOR gate, NAND gate, NOR gate. So these are the elements, and how we can make use of these elements in the design of subsystems is the main criteria we will be using. Okay, so the thing what you need to emphasize is, see how you make use of these elements. So what are the design aspects you are going to consider, so what is the constraints you need to focus on this. So all those details you need to consider thoroughly for the element by element basis, so that when you design your subsystem, or when you make use of these elements in order to design your any complex circuits, so then the realization or debugging of the circuit will be easy for you. Okay, so this is the BiCMOS NOR gate layout diagram, that is mask layout, what we can call it as. Okay, so along with this, so we go for some pseudo logics. So let's say we want to have a combination of a plus b plus c. So you want to create some adders, one bit adder you want to create. It means then we can create by using a Nmos logics. So there are other types of logics you can create it, not only along with oring the logic or anding the logic. So along with that, we can create some random number generation. So in order to create the random number generation, we can make use of the pseudocoder generators. So this is one of the form of CMOS technology what we can create in order to create a pseudocode by using a NAND gate. Pseudocode by using a NAND gate. You can see here the VSS has been grounded, and you have a N blocks. So depending upon the input what you are giving, so depending upon the combinations what you are going to use for this ABC. So based upon that, you'll be generating the random values at the output terminal Z. Okay. So this is the that is the Wien inverter, means at the output terminal what we have discussed at the Z terminal is there, right? So what will be the output at the Z terminal, you will be calculating by using this expression. So you can see here in this expression, it is mainly dependent upon your pull-up transistor, that is the impedance of the pull-up transistors and the impedance of the pull-down transistors. So the ratios what you are going to select. So based upon that, your threshold, that is a inverted voltage, will be appearing. And one more thing, important thing what you need to see is, so in the pseudocode Nmos logic, so the threshold voltage of all the transistors also plays an important role. Okay, so you can see here V inverted is nothing but VTN plus the mobility of both the PMOS transistors and NMOS transistors you need to consider, and the effective voltage which is appearing across the gate terminal, so that has to be considered. So based upon that, we can able to calculate the inverted voltage across the output terminal by using this expression. Okay. So you can see here, so what is the difference between the normal inverter and over here is, so there is one more type of driver we have connected to the output of the inverter. So in this case, you can see the input voltage inverter terminal, it is a 50% of the VDD value what you are giving across the input supply. So the inverted output at the output section, so which is nothing but 50% of your VDD value, and the threshold voltage. So since the threshold voltage, we need to consider it for the pseudo random noise generator for that. So therefore, the threshold voltage you can see here, it is 0.2 of percentage of your VDD we need to consider. So for the given consideration or for the given circuit diagram, so if the VDD is 5 volts and the mobility, that is a negative electron charge mobility, if it is 2.5 percentage of the positive charge mobility, and the pull up and pull down transistor ratio, so what we are considering, that is for the top portions and the bottom portion of your transistor, that is for the PMOS and the NMOS. So if you taken the impedance ratio is 3:1, means then we can implement these NMOS inverters which can act like a similar inverter what we have discussed in the previous slides. Okay. So this is how we can generate a possible the clock which is associated with the dynamic CMOS logic. So you can see whatever the pseudo generator whatever we have used in the previous diagram. So the same we are using. Along with that, we are making use of the contact cuts connection from the PMOS to the last NMOS transistors. So by using this, we can make use of derive the clocks in different frequency values. So basically, we will be using in a sequential circuits, we will be using a T flip-flops in order to do the frequency dividers. So by using this pseudo generator circuit, we can possible to derive from the fundamental clock into depending upon the frequencies values what we are going to select. So we can design by using this circuit diagram. So this diagram we call it as a dynamic CMOS logic. So you can see the first clock what we are deriving is it is having a fundamental period very larger when you compare to the second one. So you can see the clock 1 O1 and O2. It is O2 is nothing but just a shifted version of the O1, and the O3 what it is that it is having a higher clock frequency when you compare to the O1 and O2. And you see here the O4. So these are the different set of clock frequencies what we can generate by changing the values which is corresponding to a terminal, B terminal and a C terminal. Okay, so whatever the input you are giving, that is a phi value. So in this phi value you will be giving the fundamental frequency value. So for this fundamental frequency values, so depending upon the input terminal what you are going to over here, so you can generate a different possible clock frequencies. So this is how you can create a dynamic CMOS logic with using 3 input NAND gates. So you can see here we have made use of the transmission gate. So from this transmission gate you can see we are giving a 2 clock pulses. So one is at the bottom of the Nmos transistors and one more is across the transmission gate. So the transmission gate what we are giving, you can see the clock frequency O23 and the complement of O23 we are giving to the Nmos technology. Okay, so by using this we can able to create an dynamic CMOS logic which used to derive a different clock frequency values. Okay, so this is a corresponding diagram. So in the previous case you can see what we have used ABC, and now what we are using is we are using the same ABC but we are making use of stabilization. How? By incorporating a transmission gate. So as I said, we will be using this transmission gate in order to stabilize the input and output sections, or it is used to connect from one node to another node in the VLSI subsystem. So therefore we are using this transmission gate in order to stabilize the input and output sections of the subsystem, which is used by using a 3 input NAND gates. Okay, so this is an example for 3 input NAND gates which is used to derive a different clock frequencies depending upon your ABC values. Okay, so this is how you can make use of it. Okay, but the thing is, see, in the case of your dynamic CMOS logic, so one problem will be appearing when you want to cascade this dynamic logic. So means what? When the clock frequency phi is equal to 0, so what happens is the circuit is in the pre-charge phase. So in such a case what happens is the PMOS device, your mobility of the PMOS device will be on and your NMOS device it will be off. So because of this what happens, the conduction path will be established between your VDD and the output, so that your output will charges, that is Vout will charges to your VDD value. And when your phi value, so that is the clock frequency what you are using phi, if it is 1, now what happens is the circuit will fall in a evaluation phase. So what do you mean by the evaluation phases? So your MOS transistor, that is a PMOS transistor, will be in a off stage. So therefore your the capacitor which will be connected across the output section, so which will be in a discharging mode, So that is nothing but because of that result your device final output will be VDD Vout is equal to 0. Okay, so in such a cases what there might be an incorrect logic you may expect if it is not discharged properly. Okay, so this is how we can create a dynamic CMOS logic. So this dynamic CMOS logic it is used to store and clocking the properties of your MOS transistors. Okay, so and this dynamic logic which will be used in order to implement the logical operations which are associated with the Boolean expressions. Here we will be using, as you can see here in the previous case, the phi what we have said. This phi which will derive the NMOS evaluation transistors, and PMOS transistor we will work it as a pre-charge transistor. We will work it as a pre-charge transistors, and this dynamic CMOS technology, it will work in two modes. The one mode we call it as a evaluation mode, and one more we call it as a pre-charge mode. So in the evaluation mode, so as I told you, your output Vout output will be 0, whereas in the case of pre-charge mode, your V output will be clubbed to your VDD value. So this is what we have done with the use of this by using a transmission gate. Okay. So you can see how the dynamic logic we can create by using different types of combinations. Okay, so you can see here we have a different types of gate types are there. So as we discussed in the previous class, the type 1, type 2, type 3 and type 4, and the evaluation clock frequencies what you are going to define. So we are giving a different evaluation clock frequencies. So that is nothing but 534, 541 and 512 and 523. And the transmission gate, which is nothing but the complement of the clock what we are giving for both PMOS transistor and the NMOS transistors we are going to give. And what is the available next types. So if you give the evaluation clock, that is for the case, let's say the type 1, if I give a evaluation clock as 534 and the transmission gate clock as 541, then the allowable next type will be your type 2 or a type 3. Okay, so this is the summary of your dynamic logic circuits with respect to their types and a sequence value. Clocked CMOS logic. The next one we call it as a clocked CMOS logic. Okay, so it is also called as a C square MOS logic. Okay, so the diagram what we have written or what it has been shown in the slide. So it is a general arrangement of your clocked CMOS circuit. Okay, so it has a pull-up clock and a complementary N block pull-down structures which has been represented by using a P and N transistors. Okay, so you can see here it has a pull-up P block and a complementary N block pull down structure is there. So which has been highlighted in the diagram. You can see here the P block and the N block transistors you can have. So since A and B terminals which has been connected in a series in the case of NMOS transistors, so therefore in the N block they are connected in a parallel manner. Okay, so this is one of the simple example, that is a NOR gate only, but we are making use of this clock by assigning the clock pulses through the use of your phi and phi bar. Okay, so that is nothing but a pre-charge and a evaluation phase. Okay, so here what we will be using is, in this circuit diagram we can able to expect there is a slower rise time and fall time because of the extra transistors which has been connected in series with the output. So there is an extra transistor which has been connected over here, that is a phi and phi bar. So because of this there is a slower in rise time and a fall time as you compare to the clocked CMOS technology. Okay, so similarly, so we are going to create a clocked CMOS inverter, and this associated circuit diagram it has been given over here. So you can see here, inverter means you will be having a one PMOS transistor and one NMOS transistors. So in order to make sure that it works for the different clock frequencies, we are giving a two more clock input signals. So one is for the O bar and one more is for the O. That is nothing but we are coupling the P transistor and the N transistors. So therefore we are making the complementary clock signals. So one is will work for the pull-up transistors and one more will work for the pull-down transistors. Okay, so the working principle of this clocked CMOS logic can be summarized in this manner. So how? So when phi is equal to 0, so your circuit will work like an inverter. Why? Because your transistor, that is a Q3 and Q4. So whatever the transistors you are connected Q3 and Q4, it will be in on state. So therefore we can say this clocked CMOS circuit will work in a evaluation mode, or it is working in a evaluation mode. Whereas when your phi is equal to 0, so what happens is your circuit will be halted. Why? Because your transistor Q3 and Q4 will be in off state. So because of this, so the inverter will move into the recharge mode. Okay. So when your phi is equal to 1, so your transistor will work in a evaluation mode. When phi is equal to 0, your circuit will work in a recharge mode. So therefore what happens is when a circuit works in a pre-charge mode, your output will be remains in the previous value what it has been retained. Okay. So this is how your clocked CMOS circuit logic works. Okay. And the last one we call it as a CMOS domain logic. We call it as a CMOS domain logic. So it is also called as a CMOS dynamic logic arrangement. CMOS dynamic logic arrangement. So in this what we are going to use is, so we are going to create an alternative N transistor and a P transistor. We will be creating an alternative N transistor and P transistors in a cascaded manner, and we will be giving a clock pulses, that is phi and phi bar will be used to pre-charge and recharge the alternative N block and a P block transistors. So means what? If one block is working in a pre-charge mode means then a phi clock will be given for the corresponding pre-charge transistors. So phi bar clock will be given. So the working principles of this CMOS domain logic is that, so during the pre-charge mode, that is nothing but when phi is equal to 0, so the output of your N trees, that is a N block which has been connected, so all the N blocks will be pulled to logic 0, and at the same time the pull-up transistors all will be pulled up to the high value. Okay. Whereas in the case of your evaluation phase, when phi is equal to 1, so in this case what we are applying here, when phi is equal to 1, so what happens is the output terminals, so that is the Z where we have connected, so the output will be clubbed from VDD to Z terminal where you are connecting, that is the output of your Z where you have, right? So across this Z terminal, whatever the input you are giving across the VDD terminal, that will be clubbed when phi is equal to 1. Okay, and here what we are going to make use is the P block transistors will be generally slow when you compare to your N block transistors because of the lower conductivity in the PMOS transistors in the logic circuits. Okay, so this is how we can create a CMOS domain logic, and this CMOS domain logic, it is also sometimes it is called as a NP CMOS logic. It is also sometimes it is called as a NP CMOS logic. So it also works in two modes. So one we call it as a pre-charge mode and a evaluation mode only. But the thing is we are setting a block of N transistors and a P transistors. So if one block it is working on a pre-charge mode means then the corresponding next block will be working in a evaluation mode. So the output of the one block will be given to the input of the next block. So therefore the dependency will be exist between one block to another block. Okay, so this is the see here in the diagram what we have shown, it is a general diagram what we have shown in the N block. So this N block, it is a combination of P block PDN and N block pull up transistor.